Hola, mi clase. Yo quiero decir, yo voté. ¿Quién puede votar? Hay los, hay los estudiantes aquí uh, que puede votar. Ah, ¿Ustedes tienen esperanza hoy o no esperanza? Uh, yo pienso que yo no tengo esperanza hoy. Ah, ¿Dónde están mis estudiantes? No hay estudiantes aquí. Ah, oh well. Empezamos. Um, okay, class. Um, so today, I've got a rather short lesson for you. So short and sweet. And today is about, well, let me just do a quick review of last time um, before I talk about what we're going to do today. So last time we introduced momentum. P equals m mass times velocity. The units of momentum were kilogram meters per second. Momentum tengo una pregunta. Yo leo el chat y no sé la palabra seguros. ¿Qué quiere decir seguros? Okay. Continuo. Oh, safe. Okay. And then the total momentum of the system is simply the sum of the individual momenta. Okay. And And what we learned is that momentum is conserved in collisions. So the total initial momentum is equal to the total final momentum. And so this is the main thing, okay? So today what we're going to talk about we're just going to do a bunch of example problems. And so what we're going to do are problems that use energy and momentum conservation. Okay? That's the topic of today's lesson. Problems using energy and momentum conservation. And the key idea is this. Do not use energy conservation during the collision. Okay? Do not use energy conservation during the collision, but do use it before and or after. Okay? Do use momentum conservation during the collision. Okay? So during the collision, is energy conserved during the collision? Yes, energy is always conserved. But the thing is that in order to use the law of conservation of energy, you have to be able to account for all the different forms of energy and all the transformations that are taking place. And the problem is that during a collision, there are lots of different energy transformations taking place that we can't account for. Okay? So, for example, when two things hit each other, heat is generated. Heat is a form of energy that is very difficult to account for. Okay? Also, two things hit each other. Sound is generated. Sound waves carry energy away. It's tough to account for the energy of those sound waves. When two things hit each other, they might deform. Think about cars when they smack into each other and the metal bends. It takes energy to bend metal, so we have the energy of deformation of these cars. That is difficult to account for. So it's although energy is conserved in collisions, it's pretty much impossible to account for all the different transformations that are taking place. Okay? It is much simpler to use momentum conservation during a collision. Okay? So let's do an example to see how this works. What if we have kind of like a U-shaped ramp, okay? And we start off with a 1 kilogram block. And then there's a 2 kilogram block. And maybe the 1 kilogram block starts 5 meters in the air. And it slides down and it collides with the 2 kilogram block. And they have a completely inelastic collision. We're going to be talking a lot about completely inelastic collisions today. So if you recall, a completely inelastic collision is where they collide and they stick together. So they have the same velocity afterwards. So afterwards, we've got these two blocks, 1 kilogram and 2 kilogram. And they have a certain velocity afterwards, okay? And then they're going to slide up the ramp, and they're going to go up a certain height. Okay, and so what we want to do is we want to calculate how high do they go up after the collision takes place. Okay, now what does your gut instinct tell you? How is this height going to compare to 5 meters? Is it going to be more or less equal? Think about it. Okay, so the first thing we're going to do is we are going to use energy conservation to get the speed of the 1 kilogram block just before the collision. Okay, so this is we can use energy conservation as long as we can account for all the forms of energy, okay? And so this is relatively simple because we have the gravitational potential energy of the block becomes the kinetic energy of the block. So we have mgy equals 1/2 mv squared. It's pretty straightforward, okay? The mass of the 1 kilogram block cancels out. So we have 10 is gravity times 5 equals 1/2 times v squared. And it's quite simple to see that that means that v equals 10 meters per second. So that is the velocity of the 1 kilogram block just before the collision. So now we have to analyze the collision. And to do that, we're going to use conservation of momentum. So use momentum conservation to get the speed of the pair just after the collision. Okay? So we have initial momentum equals final momentum. So this 2 kilogram block is just sitting at the bottom of the incline. So it starts at rest. Okay. So all the momentum before the collision is carried by this 1 kilogram block, and its mass is 1, and its speed is 10. So 1 times 10 is the initial momentum. The final momentum is carried by both blocks, and they're stuck together. So they act like a single mass of mass 1 plus 2 equals 3 kilograms, and they have some final velocity. So dividing both sides by 3, the speed of the pair after the collision is going to be 3.3 meters per second. Okay? So this velocity right here just after the collision is 3.3 meters per second. And then they start to go up the other side of the ramp, or of the U-shaped thingy. Okay, and we are going to use energy conservation once again to get the final height. Okay. So what we have is we have initial kinetic energy converting into potential energy. So the initial kinetic energy is 1/2 mv squared. The final potential energy is mgy. Now keep in mind that this m is different from that m because for this energy conservation problem, we're talking about the two blocks together. So this mass is 3, that mass was 1. But regardless, in this case as well, the mass cancels out. All right, so we have 1/2 times the velocity is 3.3 equals 10 times y, which says that so we can calculate the final height. And we get 0.56 meters is the final height. Okay, so it only goes to about 10% of the original height of the 1 kilogram block. So this is a problem where we're using energy conservation followed by momentum conservation. Okay. We could also do, problems where I didn't put this in the homework, but we could also do problems where momentum conservation leads into. There's a question in the chat. Why is it 3v and not 2v? That is because both the blocks are stuck together, right? So it's 1 kilogram plus 2 kilograms, 3 kilograms is the final mass. Could also do a problem where you have a collision and then the two go off a cliff. So that would be momentum conservation transforms into a projectile motion problem. Okay, I didn't write that into the homework, but that's another thing you could do. All right, so let's do another example of energy and momentum working together. So what if I have a 2 kilogram block moving to the right at 7 meters per second, and it collides with a 3 kilogram block that is initially at rest. Okay. And then they have a completely inelastic collision. And they stick together and start headed off in this direction with a certain final speed. And then the pair of them encounters a spring. And that spring has a stiffness of 90 newtons per meter. And so our question is, how much is the spring compressed? So what we're going to do is we're going to use momentum conservation to analyze the collision. And then after the collision, these two have kinetic energy. And that kinetic energy becomes elastic potential energy. So we use energy conservation, momentum conservation, which leads into energy conservation once again. So let's figure out what is this speed after the collision. So we'll use momentum to do that. P initial equals P final. The initial momentum is mass times velocity, so 2 times 7. The final momentum, both of these two are stuck together and moving, so the final mass is 5 times v. So dividing both sides by 5, we get that the velocity after the collision is 2.8 meters per second. So after these two hit each other and stick together, they're going at 2.8 meters per second. Now we use energy conservation. So the energy of these two blocks before they hit the spring is kinetic energy. So we have 1/2 mv squared. And then after they compress the spring, all of that kinetic energy has been converted into elastic potential energy. All right. So that's 1/2 kx squared. The 1/2s cancel out. And so we can start plugging in numbers. Now, what is the mass? Well, it's the kinetic energy of both of these masses sliding into the spring, so that's 5. The velocity we just calculated is 2.8. The K value is 90. That's the stiffness of the spring, times x squared. So we can solve for x. And we get that the amount of compression is going to be 0.66 meters. All right. So I want to repeat again and again because students often do this. During the collision, you want to use momentum conservation. Never use energy conservation to analyze the collision itself. You can't account for all the energy transformations that are happening. So even though energy is conserved, you can't use the conservation of energy effectively during the collision. Okay. We're going to do another example with another completely inelastic collision. So we've got a 1 kilogram object that is moving to the right at 10 meters per second. Then there's a 2 kilogram object over here that is moving to the right as well, but only at 5 meters per second. So the 1 kilogram is going to catch up to the 2 kilogram and collide with it, and they have a completely inelastic collision, so they stick together again, and they continue now stuck together with some final velocity v. Okay, so the system starts out with a certain amount of kinetic energy, and it ends up with a different amount of kinetic energy. So the question is, by how much does the kinetic energy of the system change? So the first thing we want to do is we want to use momentum to analyze this collision. Okay? Initial momentum equals final momentum. The initial momentum is the momentum of the 1 kilogram object plus the momentum of the 2 kilogram object. So 1 times 10 mv is the momentum of the 1 kilogram object, plus 2 times 5 is the momentum of the second object. And that equals the final momentum. The final momentum is a single 3 kilogram mass, 1 plus 2, moving with a speed v. All right? So adding these two together, we get 20 equals 3v. Dividing both sides by 3 gives us 6.7 meters per second is this velocity. So this is 6.7 meters per second. So now we have to use that to analyze the energy changes in the problem. First, let's get the initial kinetic energy. Initially, we have a 1 kilogram mass. I got 3v because there's a 1 kilogram mass and a 2 kilogram mass stuck together. So their mass after the collision is 3. And then their velocity is v. So their final momentum is 3v, m times v. So in a completely inelastic collision, the two masses combine to make a single mass that's total mass is the sum of the original masses. So initially, the kinetic energy is going to be the kinetic energy of this one plus that one, okay? Formula for kinetic energy is 1/2 mv squared. So this one has a kinetic energy of 1/2 times its mass, which is 1, times its speed squared, so times 10 squared. This one has a mass of 2 and a speed of 5, so 1/2 times 2 times 5 squared. So we have to add those together. All right. So this first term is 100 divided by 2, that's 50. And the second one is 1/2 times 2, which is 1 times 5 squared, which is 25. So we start out with 75 joules of kinetic energy. Now let's look at what is the kinetic energy afterwards. Well, afterwards we have a single mass because these two masses are now stuck together. Okay. So we have 1/2 times the mass after they're stuck together is 3. And the velocity after they're stuck together, we calculated from momentum, is 6.7. So working that out, we get about 67.3 joules. So the kinetic energy went from 75 to 67.3. So that means that subtracting those two gives 7.7. This is 75, not 7.5. I accidentally put a mark there. So 75 minus 67.3 equals 7.7 joules of kinetic energy was converted to other forms. Most of that is probably heat. Okay? Most of that is probably heat. But then also some of that energy could have been carried away as sound waves. Some of it could have been deforming, the blocks. Okay? I'm not going to work out the math completely for this one, but okay, but I just want to talk about it because there's a quiz question that's similar to this. So what if we have a rock, okay, and you put some TNT into the rock. So this rock has a mass m, okay, big M. And there's an explosion. The TNT explodes. And one of the chunks of rock is sent off this way with a velocity v1, and it has mass m1. The other chunk of rock is sent off in the opposite direction. It has a speed v2 and a mass m2. Now, and the initial velocity of the system is 0. Now, according to momentum conservation, P initial equals P final. Well, the initial momentum is 0. Okay, so you have 0 equals, the final momentum is m1 v1 plus m2 v2. So that's the momentum conservation equation. Because mass is conserved, we also have that big M equals m1 plus m2. Because this is because it's the rock is blasted into two chunks. Okay, so if you had 4 kilograms of mass and I broke you up into two pieces, one of the pieces is 1 kilogram. You can deduce that the other piece is 3 kilograms. All right. If we think about kinetic energy, the initial kinetic energy is 0. because the system starts out at rest. The final kinetic energy, though, is not 0. It's going to be the kinetic energy of this piece plus the kinetic energy of that piece. So it's going to be 1/2 m1 v1 squared plus 1/2 m2 v2 squared. All right? So in this case, the kinetic energy goes from 0 to not 0. So we actually have kinetic energy. We have energy turning from one form into kinetic energy. So in this case, the chemical potential energy of the explosive became the kinetic energy of these two chunks of rock. Okay, so there's a quiz question that's similar to this, so I just wanted to talk about it so that you guys weren't completely lost. So that is my lesson for today, and I will see you in the Zoom room.